Hi everyone, my name is Vijay. As a former student of NIT Warangal and former faculty of CBIT and MESR colleges, I have something interesting to share with IIT-JEE NEET aspirants and intermediate students. As the exams are approaching for you, I am going to explain important topics in physics. I am also going to solve important problem models in those topics so that they can be helpful for the students who are preparing for the exams like IIT-JEE and NEET. Today, let us see about potentiometer. Potentiometer is a device which is used to measure EMF of the cell, internal resistance of the cell, or potential difference across any element like a resistor, like this. So it can be used to measure EMF of the cell and internal resistance of the cell and potential difference across the any element like a resistor, like this. So let us say IPQ is the current flowing through the resistor. So potential difference across the resistance means VPQ. So these three things can be measured with the help of potentiometer. Yeah. So in this lecture, we are going to see how to measure the EMF of the cell with the help of potentiometer. So that is the thing. Let us say we want to measure the EMF of the same cell like this. So we want to measure EMF of the same cell. How to measure? Let us see. Yeah. The potentiometer circuit, which is used to measure EMF of the cell, can be represented in a simplified form like this. Okay. So it consists of long wire AB of uniform cross section in series with battery E0 and rheostat R0, which is kept at suitable position so that a constant current I0 flows through the main circuit. This is called main circuit ABCDA. This is a simple circuit in which battery E0, rheostat R0 and wire AB are connected in series. Okay. In the sub-circuit, cell and galvanometer are connected in series. You can see like this. Same cell we are using that we considered above. So they are connected in series, such that junction A is connected to positive terminal of the cell and moving contact J is kept in contact with wire AB. We can see. So this is about potentiometer circuit. Yeah. First of all, we are going to obtain the expression for current flowing through the cell or galvanometer. So that is the thing. So let us say the moving contact J is at an arbitrary position. Arbitrary position means what? Yeah, it can take any value. So when it is at arbitrary position, let us say I is the current flowing through the sub-circuit. Let me name AEFJA in the clockwise direction. That is the thing. Okay, let us focus on the junction A. At the junction A, we can see I0 is the current entering, I is the I is the current leaving. Yeah, what is the current that is flowing from A to J? Let us say that is IAJ. So let us obtain IAJ in terms of I0 and I. For that, what we need to do? So we need to apply KCL at junction A. So we need to apply KCL at junction A. What the KCL states? Yeah, at any junction, algebraic sum of the currents must be 0. Let us say entering current is positive. Yeah. So let us say entering current is positive. So then leaving current is going to be negative. Leaving current is going to be negative. You can see. So here what is the current entering? Entering current is I0. Leaving current is I and IAJ. as per KCL, algebraic sum must be 0. That means in entering current I naught, that is positive. Leaving currents are I and IAJ. As they are leaving, sign should be negative. Their sum must be 0. So that means IAJ is equal to I naught minus I. This is the current which is flowing from A to J. Yeah, in order to get current expression, we need to apply KVL to the sub-circuit. To make things clear, let me draw the sub-circuit again. Here what is there? Cell and galvanometer are connected in series like this. Let us say Rj is the resistance of the galvanometer. Between A and J, what is there? Between A and J, what is there? Wire is there. Let us say Raj is the, let us say Raj is the resistance of the wire between A and J. Yeah. So this is cell. Yeah. We know, we already mentioned I is the current that is flowing from flowing in the clockwise direction. Yeah. In the wire, it is flowing from A to J. That is I naught minus I that we obtained. But we know that current always flows from higher potential to lower potential. We indicate positive sign here, negative sign here, positive sign, negative here. Current is flowing from left to right. So higher potential to lower potential. So when we apply KVL to this loop, AEFJA, what we are going to get? Minus E minus IR minus IRG plus I naught minus I RAJ equal to 0. So when we separate the terms, what we are going to get? I naught RAJ minus E is equal to I terms we have 3. R plus RG plus RAJ. So that is what I is equal to I naught RAJ minus E by R plus RG plus RAJ. Yeah. So this is the current expression. Let me move to next whiteboard. Yeah. So we obtain current expression. I naught RAJ minus E R plus RG plus RAJ. What this term represents? For that we need to refer to Ohm's law. Yeah. So let us say we know that Ohm's law relates to current flowing through the resistor and potential difference across the resistor like this. Right? So like this, when I is the current flowing through the resistance R, when V is the potential difference across the resistance R, they are related by Ohm's law like this. I is equal to V by R. Okay. What is that V? V is equal to I into R. We can see from this. Where V is potential difference across the resistor. I is the current flowing through the resistor. Here you can see in the product what this, when there is a IR product is there means what that I indicates. I is the current flowing through the resistor. I is the current flowing through the resistor. Same we can apply to I naught RAJ. In I naught RAJ, what is that I naught? I naught is the current flowing through the resistor RAJ. Right? What this product what this product what we can say, what this product indicates. Okay, what this product equal to, more precisely, it is equal to potential difference. Here also I naught RAJ product is equal to what in this expression? I naught RAJ product is equal to potential difference across the resistance RAJ from Ohm's law. But this resistance is present between junction A and moving contact position J. Potential difference across the resistance means that is also going to between going to between A and J. So this is going to be VAJ. So what this I naught RAJ represents VAJ. Potential difference across the junction and moving contact position J. That is the thing. Yeah. But what is our objective? Our objective is to find cell EMF. Cell is going to have fixed value of EMF. It may be 1.5 volts or 2.1 volts or something like that. It is going to have fixed value of EMF. Okay, right. Before going to experimental procedure, let me make certain things clear. So for that, let me draw the circuit again. Yeah. So this is main circuit of the potentiometer. So that current I0 flows through it. In the sub-circuit, we have cell and galvanometer in series. Yeah. When we move the moving contact J on the wire AB, what happens? We can observe wire AB there. When we move the moving contact J on the wire AB, what happens? Here, the position of the what is called junction is fixed. We can say junction A position is fixed. When we move the moving contact position J, what happens? The length of the wire between junction and moving contact position varies. So when that varies, what happens? Resistance also varies, which is proportional to length of the wire. So that we can say here what we are doing. So when we move the moving contact J on the wire AB, so here you can see length of the wire between A and J. So that is going to vary. When length of the wire varies, the resistance which is proportional to length of the wire also going to vary. And potential difference also proportional to RAJ, we can see. So that is also going to vary. This is what going to happen when we wear the moving contact position on the wire AB. Yeah. So let me take it as equation. This is 1. So this is 2. So let me write I is equal to, when we substitute VAJ minus E by R plus RG plus RAJ, this is 3. So when we vary the moving contact position, this is varies. VAJ varies. Yeah. Okay. So in the when we move the moving contact, VAJ varies. In the range of variation of VAJ, EMF value is going to present. Like that they design. Okay. Let me make it clear through example. So let us say VAJ varies when we move the moving contact from 0 to 5 volts. And EMF value is 2.1 volts. Right? So you can see 2.1 volts is present between 0 to 5 volts. Right? That means for a particular position of moving contact, what happens? This potential difference is going to become equal to the EMF. So then what happens? Then you can see from the equation 3, when VAJ becomes equal to E, what happens? Current becomes 0. Right. How to detect that zero current condition in the sub-circuit? Yeah. So zero current condition is detected with the help of galvanometer. You can see in the potentiometer, galvanometer is present to detect that zero current. Okay. So that will zero current that is present in the sub-circuit. Right. Now we are in a position to understand the experimental procedure. Yeah. The experimental procedure is to move the moving contact J on the wire AB and obtain the zero deflection of galvanometer for a particular position of moving contact. We move the moving contact on wire AB. Let us say for a particular position, it shows zero deflection. Okay. So that at that particular position, what happens? Yeah. EMF becomes equal to potential difference between the junction and particular position of moving contact. Now you can understand. I will tell. So right. So let us say at a particular position of moving contact, let us say 1. Galvanometer shows zero deflection. That means current becomes 0. Yeah, let us say that particular position is 1. So that means when J is at position 1, galvanometer shows 0 deflection, current becomes 0. So when we substitute into equation 3, what we are going to get? 0 is equal to VA1 minus E by R plus RG plus RAJ. You can see, as LHS is 0, we are going to get E is equal to VA1, which is equal to, from this expression, when we substitute J is equal to 1, we are going to get I naught RA1. You can see. Yeah, so this is equation 4 we can take. Yeah, right. So when you can see from the equation 3, when current for a particular position of moving contact, when current becomes 0, what is happening? EMF is becoming equal to potential difference between junction A and that particular position of moving contact. That is E is equal to VA1, right? So now you can see from the expression 4, by measuring I naught and RA1, we can obtain EMF. That is our object. Clear? But standard practice is to replace the cell with standard cell, whose EMF is known, and again repeating the experiment. Right? Yeah. So let us replace the cell with standard cell. So this part of the potentiometer circuit is going to be same main circuit, so that constant current I naught flow through it. So this is R naught rheostat resistance. In place of cell, we are going to use standard cell, whose EMF is known. Let us say ES is the standard cell EMF, RS is its internal resistance. Yeah. So these are. So what is our current expression for this? We can going to get. So we, from equation 3 we can write I is equal to VAJ. In place of cell parameters, we are going to get a standard cell parameters. That is the only difference. In place of V and R, we are going to get ES and RS. That is the only difference. As we replace the cell with standard cell. Yeah, let us. This is 5. Repeating the experiment means what? Right. So we move the moving contact on the wire AB and obtain the 0 deflection of galvanometer for a particular position of moving contact. So that at that particular position, yeah, EMF of the standard cell becomes equal to the potential difference between the junction and that particular position of moving contact. That is the thing, right? So that means, let us say that particular position is, for this case, 2, at which galvanometer shows 0 deflection. So when we substitute these values into the above expression, what we are going to get? So 0 is equal to VA. In place of J, we have to substitute to ES, RS plus RG. In place of J, we have to substitute 2. Na? So here also RA1 here. Okay. So as LHS is 0, we are going to get VA2 is equal to, sorry, ES is equal to VA2. But VA2 we can write from the equation 2, that is I naught into RA2. So that is the thing. This is we can take as equation 6. Right. You can see in the EMF expressions. So we have EMF expressions are only depending upon main circuit current and resistance of the wire in between junction and moving contact position, not on internal resistance. Internal resistance is not involved. Okay. One more thing. When galvanometer shows 0 deflection only, we are getting EMF value. That means when the potentiometer measures the EMF, okay, the current drawn by the sub-circuit is equal to 0. Okay. So these two things we can observe. Okay. One more thing here, a scale is kept below the wire AB. So this is scale. So with the divisions marked on it. Yeah. To measure the length of the wire between junction A and moving contact position, for which galvanometer shows zero deflection, means 1 here in the first case. LA1 we are going to measure with the help of scale. Here also in this case, LA2 we measure with the help of scale, which have to be used in the next part. Okay, let me move to next whiteboard. Yeah, so we obtained E is equal to I naught RA1, ES is equal to I naught RA2. But what is RA1? Resistance of the wire between junction A and moving contact position 1. So that is rho LA1 by resistance of the wire is given by rho L by A. So here A we use na. Let me take A dash, where rho is the resistivity of the wire, A dash is the area of cross section, LA1 is length of the wire between A and 1. Right. So when we substitute, what we are going to get E is equal to, similarly RA2 is equal to, as the same wire is used, we are going to get rho and A dash are common. Same in the two cases we use the same wire AB of uniform cross section. Therefore rho and A dash are common. So E is equal to I naught when we substitute rho LA1 by A dash. Here you can see these are all constants. I naught rho A dash. Yeah. Here I naught main circuit current is going to be constant throughout the experiment. So you can see that means, yeah. So let me take it as constant A. So that implies E is equal to A into A1. Sorry, LA1. A into LA1. Right. Similarly, ES is equal to, when we substitute what we are going to, same we are going to I naught rho A dash. Here we are going to get LA2. So that means ES is equal, we are going to get as A into LA2. So this is A. You can see. So this is proportional to LA1. Okay. Here also ES is proportional to LA2. Right? So that is the thing. So when we take ratio, what we are going to get, E by ES is equal to LA1 by LA2. Yeah. So E is equal to ES into LA1 by LA2. So here you can see ES is known, standard cell EMF is known, and these are measured from the scale. So by substituting this, we can obtain the EMF of the cell. You can see in the experiment we are only measuring LA1 and LA2. The length of the wires for which galvanometer shows zero deflection in the two cases. By measuring this, we are obtaining the what is that, cell EMF. Okay, right. So today we have learned about how to measure the EMF of the cell by using potentiometer. The working principle is, when the galvanometer shows zero deflection, EMF becomes equal to potential difference between junction A and moving contact position. Thank you.